Hello, everyone. We're now going to start with part 2 of module 2, where we're going to continue our discussion of property diagrams and specifically the TV diagram that we were working on last time. So as you can see, I've redrawn the diagram in a simpler way with just the lines describing the process of increasing the temperature of water inside a piston cylinder. So just think of part 1, look at your final diagram in part 1 and how we got this diagram, and the diagram here is showing exactly what is happening in that case, but a little bit simpler without all the annotations on it. And we know that the pressure was 1 atmosphere, and I added that this pressure is also equivalent to 0.1 megapascals. And we can add to this that the temperature of saturation here was equal to 100 degrees Celsius. Now, what we can do is, what if we changed the pressure, the initial pressure on the water? So in our piston cylinder assembly, what if we said that the pressure now on the piston cylinder, instead of being 0.1 megapascal, the pressure could be equal to 1 megapascal, or 10 times atmospheres. So pressure would be equal to 10 atmospheres. What would happen to our graph? Our graph would actually be shifted to something like this. So it would shift up, and we would actually get a new diagram where the pressure is equal to 1 megapascals. And if we went even higher with our pressure, let's say our pressure now would be equal to 8 megapascals, we now would go even higher in our diagram. So something like this. Okay, and this would be a pressure is equal to 8 megapascals. Now, all this data is gathered experimentally, so it's all experimental data. So that's really important to note, is that it's all experimental data. And now that we're trying, so the temperature saturation, for example, for 1 megapascal would be equal to 150 degrees, for example, and the temperature of saturation for 8 megapascals could be equal to 300 degrees. These numbers are made up, but it's just an idea of what could happen. Okay, and I'll leave these out just because it's not the best illustration, but the temperature of saturation would increase. Now, what happens is we can do all these experiments at many, many different pressures, and we can actually come up with a curve that can be fit through all these points right here. So our curve looks something like this. And all these experiments are done with water, okay? So this is all the experiments with water. Now, you can do it with different fluids, but this specific chart is for water. And we can see that for water with different pressures, we're able to get sort of envelope of what is happening. And this envelope is essentially gathering where the shifting points from saturated mix to superheated vapor and to compressed liquid are happening. So what we can say is that this region inside the bounds, so this region inside of here, okay, so I'm just going to draw this here like that, so we know that it's this region. This region can be called the saturated mix region, or the saturated mixture region. Okay, so inside the region we have saturated mix. On the left of this region, anything on the left of this region, at any pressure we're given, we know that it's going to be below saturation temperature, so the temperature is going to be below. So what region is that? The region here is called the compressed liquid region. Anything to the left of this bound is going to be a compressed liquid. And anything to the right of this bound is going to be the superheated vapor region. So we see that with this graph, we're able to essentially create a graph for different water pressures, a general graph for different water pressures that is essentially occurring. And we're able to find, if we have, let's say, an operating point that's somewhere here, we can then find, from that point, we can find the temperature, the volume, as well as the pressure of that point. Okay? Now, when pressure reaches 22.6 megapascals, so I'll write it down. When pressure reaches 22.06 megapascals, we observe that there is no constant temperature vaporization process. So what does that mean? So if we look at our diagram above, we notice that this region tops off at the end here. So at the end here, there's a top off in that region. There's a point where it reaches the top. So let me redraw the graph below so that it's easier to see. And then I'll draw it a little bit smaller. So if we have our region like this, at 22.06 megapascals, we actually have the line that connects with the top of our graph. So this would be pressure is equal to 22.06 megapascals. And this is for water, okay? This statement is for water. Okay, this statement is true for water. And at pressure of 22.06 megapascals, we find that there is no constant temperature vaporization process. So before that, if you were at lower pressure, we would have this region here where we had a constant temperature boiling process. Okay, the line would look something like this. We had a liquid starting at this point here. It would heat up until a point where it starts boiling. Then during boiling, the temperature would not change. And then finally, when everything was boiled off, the temperature would start increasing again, as well as the volume. When you reach 22.06 megapascals, the fluid essentially turns from a liquid to a gas instantaneously. And that is called the critical point. So this point here, okay, so this point here that I'm pointing at with the red arrow is called the critical point. It's all right, it is called the critical point. And this is a point where vaporization occurs instantly. So in an instant, it happens immediately. And this critical point for water, the critical point, it has a pressure critical that is equal to 22.06 megapascals, which we've already talked about, which is a very high pressure when we look at it, okay? 22.06 megapascal is a very, very high pressure. And the temperature critical at which the vaporization occurs at 22.06 megapascals is 373.95 degrees Celsius. Okay, now what happens if our water pressure is greater than P critical? What would happen if our water pressure is higher than critical? Let's say it's at 25 megapascals. So let's draw it. If we had a 25 megapascals, it would look something like this. Okay. How do we determine the phase above 22.06? It's actually impossible to determine the phase at that point, except looking at it visually. We don't know whether the shift happens here, or here, or here, or here. We don't know where the shift happens for vaporization when we're above the critical pressure. So we can say that if pressure is above pressure critical, we cannot determine phase. Now, this concludes our discussion of TV diagrams. The next diagram I want to look at is a PV diagram. So instead of having a TV diagram, what if we had a PV diagram? So a PV diagram is just pressure versus volume, and we're interested in using a PV diagram for studying the variation of properties just by looking at a different type of experiment. So let's say our experiment now is modified a little bit, and we have this piston cylinder assembly the same way as before, and our initial pressure is 1 megapascals, and our temperature is equal to 150 degrees Celsius. Okay, so now we're going to do a different type of experiment where we're going to look at PV and use a different experiment type where we have our temperature stays constant. So T stays constant. And what we're going to do in order for temperature to stay constant is we're going to add a heat to this, but the pressure of 1 megapascal is created by adding blocks on top of our piston cylinder assembly. So above our piston, we have blocks of weight that are adding that pressure of 1 megapascal. Now, what happens when you start taking off the first block? If you take off the first block, what's going to happen is your piston is going to move up a little bit. And that piston moving up means that the pressure is going to decrease a little bit. So if we look at, so that would be a first case. Then if we go and take off a second one and then a third one, what happens to our system? Well, what happens is if we keep the temperature staying constant by adding heat to supply more heat while the piston moves up, okay, if we decrease the pressure and increase the volume, the temperature would also decrease. Okay, so if we didn't add heat, the temperature would decrease a little bit. So what would happen is you would have a pattern that looks something like this. Your pressure would go down and your volume would go slightly up. Then your pressure would stop going down during saturation. So during the phase where you have saturation, and then finally the pressure would go down even more once we reach that saturated mixed region. And that would be at T1 is equal to 150 degrees Celsius. Okay, so temperature would be equal to 150 degrees Celsius. Now, by taking off these weights and decreasing the pressure as we go, so by taking off the weights, you decrease the pressure as we go and keeping the temperature constant, what we're actually seeing is we're seeing compressed liquid, which is at high pressure, and we're decreasing the pressure, so we're allowing the liquid to become a gas. So essentially what's happening is we have boiling occurring here. Remember that the higher the pressure, the more likely something is supposed to be a liquid. Okay, the more compressed it is, therefore the more it's going to be a liquid. So at the start, what we have is we have a compressed liquid in this region here, and then that compressed liquid starts boiling up until we reach superheated vapor in this phase here. And so if I just erase these arrows just for illustration purposes and making sure that we don't, so let me just put little arrows here so that we can see the direction. And in the same way as before, if we start doing the experiment at different temperatures, we could have another line that looks something like this. And we're going to be able to draw another region like this with our saturated mixed region in the middle, our compressed liquid on the left, so compressed liquid is all here, and our superheated vapor on the right. And do not worry too much if you're not 100% sure what's happening right now, but the idea is that if we have pressure and volume, we can find temperature. If we have temperature and volume, we can find pressure. If we have pressure and temperature, we could also find volume. So that's the great thing. If we have the pressure in our system and the volume in our system, we can find anywhere on this graph, we can find the temperature of our system and vice versa. So it is a very useful tool. Okay. And this tool, these two diagrams are actually going to be mapped. So we're going to map these two diagrams with all the points on the diagram. So every single point on the diagram that you have, and obviously not every single point, but a lot of points on the diagram are going to be mapped onto, so let me change back to white, are going to be mapped onto our thermodynamic tables. And if you haven't already checked them out, in our module, we have available Appendix 1. And Appendix 1 has our thermodynamic tables. So if at this point in the lecture you do not have Appendix 1 downloaded, please do download it, pause the video, and come back with your tables. We're going to be using them in a little bit, not immediately, but it will be useful to have those tables available. Okay, so moving on from this, we also can make, instead of a TV graph, so with temperature and volume, we can also make a T specific volume graph. So remember, V is equal to specific volume. So lowercase v, and if you remember, V is equal to volume over mass. Specific just means that it's divided by mass. So we know now, if we have a TV diagram for a specific substance like water, we have a TV diagram, we know there's a region like this, and we know that we can find, because we have this graph available in tabular form, we can find any point on this graph, we can find what the properties would be. So if we have temperature and volume, we can find pressure. If we have pressure and temperature, we can find volume, etc., etc., etc. But in this case, we're going to be finding specific volume. And specific volume is very useful because you don't have to have the same mass for the graph. So it's independent of mass, which is great. So you can have different amounts of mass of water and it's still, the graph would still apply. So we know that from this graph we can find, and I'll write it down, we know from this graph we can find pressure, temperature, and volume. But how do we determine volume in the saturated region? How do we determine volume in the saturated region? So inside the saturated region, remember, let's say we have a certain pressure that's going to be constant because we're saturated. We have this line that goes through the saturated region at different pressures, right? So we have this line, we have a line above, below, for the different pressures. So in the saturated region, we remember that we have and I'll add the fully, so saturated mix region, we have a mix of liquid and gas. And remember that saturated just means boiling. So anytime your fluid is within the region inside, so the region highlighted in red right now, we have boiling, okay? And depending on the temperature and the specific volume, the boiling can be different. Now, let me just erase the reds. So how do we determine the volume within that region? So try to think about how we could determine the volume within that region. So the volume within that region is going to be defined by three different points. So we're going to have, let's say our operating point right now is going to be highlighted in red here, and it's going to be point A. And what we can say is that point A is between these two bounds here on the outsides. And we're going to call this bound here VF, and we're going to call this bound here VG. So VF for V fluid and VG for V gas. This is an old notation, so they just use fluid for liquid, which can be kind of confusing, but if you just remember VF, essentially VF designates designates, not designated, designates the saturated liquid volume. So it's the volume where we have a saturated liquid. So remember, saturated liquid is when our saturated mix is 100% liquid and we're right at the point where it starts boiling. And this, remember, x is equal to 0 here. Okay, our x is equal to 0. Now, Vg is determined as the saturated vapor volume or gas. Okay, vapor and gas are the same thing. And here, x is equal to 1. So when Vg is achieved, we know that we have 100% gas, and now we're just at that point we're done with boiling, and anything above that will increase the temperature and the volume. Okay, and obviously in our diagram we can say that point A indicates that there is a condition that is part liquid, part vapor. So how do we determine how much of the region is part liquid and how much of the region is part part vapor? So if I'm going to copy over the diagram. I'm going to recopy the diagram over lower so that we have it. Okay. So we have the diagram again. And let me just erase the little dots here. And what we can say from this diagram is, I'm just going to replace the A on top so that it doesn't. So what we can say from the diagram is that if we define this point as V, or V, our V that we're looking for, we can say that this spacing here is V minus VF. Okay, so if I zoom in, we have V minus VF between this space. Okay, that's the spacing between the two. Okay, so we can go ahead and sort of derive how to figure out what our V is going to be equal to. This is what we're looking for, V right here. So we can say, we can start with total volume. And we can say that total volume is equal to V liquid plus V vapor, right? The total amount of water we have in a piston cylinder assembly that is part water, part liquid is going to be the volume of the liquid plus the volume of the vapor. And we can rewrite this in terms of our specific volume. And specifically, we can look at the specific volume of fluid and the specific volume of gas. So if we remember, specific volume is equal to V over M. So we can say that V is equal to M times specific volume. So we can say that the V of the liquid, the volume of the liquid, is actually equal to mass of the liquid times VF times the specific volume of the liquid. And the mass of the vapor is multiplied by Vg, because that's a specific volume of the gas. Now, if we now say that our V here, V is equal to V over M. So now what we can say is that if we divide everything by M, so we're going to take this equation up here and we're going to divide everything by M. So we're going to say V over M is equal to M liquid. And remember, this is M total, right? This is V total over M total is equal to V. This is the whole volume of the whole, the specific volume of the whole mix. So we have V over M is equal to mass liquid times VF divided by M plus mass of vapor times Vg also over M. And now we can say that this is also equal to V. So we now have an expression for V that says V is equal to mass of liquid times Vf over M and mass of vapor times Vg over M. Now, something interesting out of this. What is this equal to? Mass of vapor over M. Mass of vapor over M Let me write it in white. Mass of vapor over the total mass of the mix is equal to X. We defined it as X. Remember, that was our quality. And what we can say too is that what is the mass of liquid? What is this part here? What is the mass of liquid over M? The mass of liquid is essentially 1 minus the mass of vapor over M. So we can say that the mass of the liquid is essentially mass minus the mass of the vapor, right? It's the total mass minus the mass of the vapor over M, which essentially this is equal to 1 minus X. So we can rewrite our expression as V is equal to 1 minus X times Vf plus X times Vg. And this equation is valid within the saturated mix region. Okay, so within the saturated mix region, where we have an X, we're able to determine from the quality, remember X is equal to quality, from the quality we can find Vf, Vg, and then finally V. Or the other way around. If you have your specific volume from the graph and you're trying to find the quality, you can find the quality from the volume. So you can use this equation and rearrange it to find X. So you can use this equation to rearrange and find X. So one thing that's for sure is that in the saturated region, which is also the region where everything boils and stays at constant temperature, in the saturated mixed region, we can say that we need to know the quality in order to find V. So essentially what that means is that if we have a pressure of 1 atmosphere, for example, looking back at our example from last time, and a temperature of 100 degrees Celsius, how do we find V? So if we look at our diagram, remember we have our diagram like this on the TV diagram. We have 1, 2, 3, 4, and 5. And we know that this is a line of pressure 1 atmosphere constant. So if we're in this region here, and we have Tsat happening at 100 degrees Celsius, how are we supposed to find the volume? The volume could be anything within this region, right? Our actual water could be at 0.2, or it could be at 0.3, or it could be at 0.4, or it could be anywhere in the middle here. And it would have exactly the same pressure and temperature. So you cannot find V without X. We need quality in order to find V. If you don't have quality, you can't find V. And the great thing is that for every saturated region, we are given in our tables. So in tables Appendix 1, and again, we'll look at those a little bit later in this module. In tables Appendix 1, Vg and Vf are given. So we know the bounds of 2 and 4. And if we have quality, then we can find what the specific volume is. Okay? And remember, all these tables are experimental. So there's no equation that can help you find the specific volume just from a simple equation. You need to use experimental tables to find Vf, Vg, and then from Vf, Vg, if you have the quality, you can find V from this equation. Okay, couple of comments about quality in general. And these comments are sort of rules that you have to follow. Quality, first of all, has meaning only for saturated mixtures. So anything outside of the region of the saturated mix, so if I were to draw the region here for different pressures, anything outside the region, anything outside of this region, the quality does not exist. Quality is only important for saturated mixes. When we have a mixture of vapor and liquid, okay? That's very important to know. And as a second point, as a follow-up, essentially what you would write is that quality is not applicable for superheated vapor or compressed liquid. Okay, so that means that quality is not applicable for superheated vapor. So quality essentially in our graph above starts at 2 and ends at 4. Okay, those are the bounds of our quality. And the value of the quality, since quality is sort of a percentage mass of vapor over mass total, the value of quality is between 0 and 1. Okay, so the value of quality is between 0 and 1. And remember, just as a quick example, X is equal to the mass of vapor over the mass total. And if we have mass is equal to 1 kilogram and the mass of liquid is equal to 1 kilogram and the mass of vapor is equal to 0 kilograms, what do we have? We have a saturated liquid. So at that point, we have a saturated liquid, and in our diagram, that would be 0.2. We just reached saturation temperature, and we still have 100% liquid, 0% vapor, therefore it's 0 over 1, therefore X is equal to 0. Then at 0.3, we have a mix between vapor and liquid, so our X might be 0.5 or 0.6 or 0.4. And then eventually, when everything is turned to vapor and we're still at the same temperature, still at the saturation temperature, we now have a quality of 1, and that would be our maximum quality. Now, the same exact rule applies for two different terms that we're going to define later on in the semester. So later on in the semester, we're going to work on different things in addition to just specific volume. And those two things are called internal energy and enthalpy. And we'll define them a little bit later in the semester, but essentially internal energy and enthalpy works exactly in the same way as our specific volume from a graph point of view. So if you had a graph of temperature versus internal energy or temperature versus enthalpy, in the saturated region, you would find your internal energy or enthalpy by the same rule. And internal energy is, so this is specific internal energy and specific enthalpy. So the units are kilojoules per kilogram and kilojoules per kilogram. Again, you don't need to know this right now, but this is just in order to do your study problems, you might need to know how to find internal energy and enthalpy from our thermodynamic tables, but you won't need to use them in a theoretical manner. So the same equations apply. So U is specific internal energy. It's a little u. U is equal to 1 minus x times UF plus x UG. And same thing for H, which is our specific enthalpy. H is equal to 1 minus x times HF plus x Hg. So you can treat enthalpy and internal energy in the same way in terms of finding their values within the saturated mixture region. So the next thing we're going to do is we're going to be looking at our table of thermodynamic properties. And what we're going to do now is we're going to take a break from part 2 and go into part 3 so that part 3 starts fresh with our table of thermodynamic properties. So now that we've defined how to find stuff on our graphs and understanding our graphs, we're going to go to how to use the table of thermodynamic properties, which is essentially a representation of our graphs, to solve some example problems, as well as trying to understand what is happening. So please get your Appendix 1 ready for part 3, and I'll see you in part 3.